All right, record is on, and this is what we have. I cannot see anything because now I just wish to see my own screen, but I cannot. Perhaps I can. Okay, so we construct the influence line by plotting the values of the design functions. Now the design functions would mean the reaction of your structure, the internal shear force anywhere, or the internal moment anywhere. Now these design functions will change their values when we move the load around. So when we move the load around and the design function changes the values, we plot those values with the location of the load that we move around. The results of that is something we call the influence line. Okay, so let me recap again. This is the influence line of the reaction at A, which means that this is the graph that shows how much RA changes when the load moves from, the near end of the structure to the far end. And this is the reaction RB. How much RB changes when the load moves from the left side to the right side. This is the shear force, internal shear at midspan of the beam when we move the load around. And this is the internal moment at midspan, how it changes when we move the load around. Okay, now the bottom line is, if we have to place the load one time and cut the free body diagram like this, like what we did in the first session, like this, it would take forever to construct the influence line for one design function. Okay, so good engineers, they're not going to do this. They're not going to tolerate this, right? So some time ago, this is a definition where you can read it, right? There's this guy, Professor Heinrich Müller-Breslau. Sounds like Polish. Yeah. He came up with the principle that says, if a function at a point in the beam, such as reaction, shear, or moment, is allowed to act without restraint, the deflected shape of the beam represents the shape of the influence line of that design function. See? So if you want to know the shape of the reaction, the shape of the influence line of the reaction, you would allow the reaction to act without restraint. You would see that the deflected shape of the beam represents the shape of the influence line. So when you have just the shape of the influence line, we call that the qualitative influence line. You will get the shape, but in order to get the numbers into the shape, or the quantitative one, we need to do some further calculation to determine the coordinates. Okay, so let us come back to this again. All right, so when I look at this structure and I want to have the influence line of the reaction at A, I would allow the reaction at A to move freely without restraint. So what's going to happen? If this is my beam, I have to draw it with some thickness, okay? This is my hinge, that's my roller, and that's my reaction. Let's say if this is my RA and I want to allow it to move without restraint, what do I do? So that would say simply that RA would need to be able to move up and down, right? That is the meaning of move freely without restraint. So I can just remove the restraint of the reaction RA. Now, what is the restraint of the reaction RA? When you have the RA, it means that you don't have the vertical movement at A. So to allow RA to go free, I have to remove the vertical restraint, and therefore it's like I have the roller in this direction. I no longer have a hinge, I have a roller instead. And when RA is allowed to move freely, it will therefore push this beam up like this. Oops. You see, because now RA moves freely in its own direction, which is the Y direction. So your beam now, when you allow this to happen, it means that your beam becomes unstable, you know. But yeah, that's what the principle says. So the deflected shape is like a straight line because in fact your beam is unstable. And look at the shape. So this is the shape, right? In the end, this becomes the deflected shape of your beam when RA is allowed to move freely. But you can see the green line here, right? That becomes the shape. So that is the shape of the influence line of reaction at A. So now you know the shape. What about the magnitude? Because you know that when you place the unit load on top of A, RA must be equal to 1. So that's the location where you can calculate the RA very easily, right? And this has to be 1. I can say RA is equal to 1 when unit load is placed on top of A. So you can get the value very easily after you get the shape because you just place it on top of A. Now you know RA is equal to 1 when there is a unit load on top of it, right? And we can do the same. Same beam. Can I do this? Copy. Paste. Yeah, there's another one. Okay, for the next shear. All right. So now RB. When I allow RB freedom to move freely, again, it's just like I add the roller here. Okay, because RB prevents your vertical displacement. So when I want to move RB freely, I must remove the vertical restraint. It's like adding a roller in that direction. And as a result, the beam will move freely like this. Okay? And this becomes a deflected shape, and hence the shape of the influence line of RB. And I can just say, okay, now the influence line of reaction at B, just like this. Now I know the shape, I need to find the magnitude. And I know that when I place the unit load on top of B, RB will be equal to 1, right? So now I know that this is 1 because for the same reason, RB is equal to 1 when unit load is placed on top of B. Okay, so far so good, right? Now this. Need to copy one more time for the moment, right? Boom. All right, thing in place. Need to move this. Now the next target is the shear, right? So I want to move the shear freely. Now the shear is a bit more tricky now because when you want to move the shear freely, what's going to happen? Let's say we consider the positive shear, right? We're going to allow the positive shear to move freely. So it's moving up on the left and moving down on the right. So if you can see the shear now, if you look on the right side of this piece, there's too many colors on. If I look at this piece, okay, if I allow the shear to go free at midspan, the shear is now on the right, correct? So it's going to be this downward shear. Because for this, I can write it again. You see, the positive shear here must be downward. And for the left one, for the right one, I'm sorry. The positive shear now is on the left surface. Now that is a positive one, so it has to be up. Okay, so it's up for this right portion. Or you can just say I look at a bit at the portion, small portion in the middle, and apply the positive shear like this. So that means in order to maintain equilibrium, on the left is going up, so this goes down, goes back to this member. And this because of the positive shear in the middle, on the right surface, it goes down, so this one goes up. Okay, so now we unlock the restraint of the shear. So we allow these vertical forces to move freely. So it's just like we add the roller here, right? So we have the downward force. So when the downward force moves freely, this piece comes down. This piece goes up. Right? Or yeah, it should be okay. So that's why the shape of the influence line of the shear in the middle looks like this. Oops, sorry, slip of the iPad. Okay, so this is the influence line of the shear at midspan. And that's the correct shape. Now you wonder about the magnitude. Because we use the unit load, you see the change of the shear in the middle here must be equal to the load, right? So you can say, because of this, I know that this is equal to 1. Because it's at midspan, so the distance on the left and distance on the right, they are equal. So you know, in order to have the equal distances, this has to be minus 0.5 and this has to be 0.5 in order to have the magnitude of 1, the change of the shear at midspan. Right? I can say the change of shear is 1. Let's make it more visible. Okay, change of shear is 1. Now, the last one, the moment. Is there any question on the shear? Anyone? Hello? Okay. Don't hesitate to ask, okay? I'm trying to go as slowly as possible. Try to write more to help you, your understanding. Let's hope it helps, okay? Now the last one, the moment. Again, in the same fashion, I want to allow the moment in midspan to move freely without restraint. So what does that mean? It means that if you want the moment to move freely, it means that that portion must be able to rotate, right? The moment is about rotation. So when you want it to move freely, you want it to rotate, and therefore you add a hinge. And again, we are talking about the sign convention of the positive moment. That is a positive one. So you can look at this as the two portions. If you want the moment to move freely, look at this segment on the left. The positive moment now, you see the moment is on the right. So it's this one. Another one is on the left. So basically it's this one. I wonder how I cannot connect them. Okay, let's do it this way. Okay, right, you see that? So when we are back here, this would be the moment in this direction and in that direction. Or you can just say, okay, you can just look at the middle piece and apply the positive moment like this. Oops, that's that, right? And in order to maintain equilibrium, you must have the moment that is equal. Is it the end of it? Okay. And opposite. Yeah, it's pretty similar in the end, you know. Here. So now, when you apply the moment and you no longer have the restraint because you add the hinge, it will move freely, resulting in, you know, this segment will go up like that. It's like you're trying to open the door, you know, and this is the hinge of your door. It goes up like that. Okay. So that now becomes a shape of the influence line of moment at midspan. Okay, now it's a shape. The question is, what about the magnitude? Now there's no two ways about the calculation of the magnitude of the moment at midspan, except to use your free body diagram. So to obtain the value, apply the unit load to calculate moment. Remember, this is the influence line of the moment at midspan. You can apply the unit load anywhere you like, but you need to calculate the moment at midspan. So I can just say, I'm going to do this. Oops. The easiest way for me is just to apply the unit load at midspan and calculate moment at midspan. And by now, when you have the point load at midspan, the moment at midspan, you should know moment is equal to PL over 4. P is 1, L is L, so this becomes a quarter of an L. So that's how we obtain this value. Okay? So that is the value coming from the calculation of the moment at that location. No two ways about it. That's it. The Muller-Breslau principles. Is there any question? Just one principle, right? Principle, not principles. Principle. See, we have the more exciting example coming up. So if you have any question now, don't hold your breath. Fire them. Don't hold your fire, I should say that. Fire the questions now, if there is any. Hello? Crystal clear? Okay, so let us see this. Now, I'm not going to give you the simple beam, am I? Because that would be boring. So we're just going to come up with the determinate structure, but with more challenges like this, for example. So now we are going to try to make use of the principle of Professor Heinrich Muller-Breslau to come up with the shape of the influence line and, of course, the magnitude as well. So now I have plenty for you to ponder. See that? RB, RD, VA, VB to the right, VC, MA, MB, and MC of this stuff. How about that? Okay. So, ladies and gentlemen, we are no longer calculating the reactions and stuff. Now we want all the values of the reaction when we have the unit load here, there, and everywhere on the beam. Okay. Are you ready? I think so. Because if you say you're not ready, what can I do, right? Okay, so let us go. Okay, now let's go with RB first. If I want RB, the influence line of RB, I must allow it to move freely, right? Now it's not straight. It's a function that allows me to change this into a straight line, right? I don't know how. Maybe I have to for a long time. Yeah. Okay. Wow. Cool. Right. So now I want the RB to move freely. Okay. Remember, I still have this. So when RB move freely, you just go like this, right? Because we have a hitch. So it will go up like that. The dotted line will not come straight. Okay. So that's how it's because RB is now free to go without restraints. It moves up freely. So I can just now draw a straight line. Okay, so the shape of the influence line becomes this one. Good. Not like that. Okay, anyway. So now that becomes the influence line of reaction at B, right? So now that's the influence line. I might as well erase the force here and then the hinge here. So this is the influence line of RB. That's the shape. Now, what about the value? Now I know that when the unit load is here right on top of B, surely RB has to be equal to 1, right? So that means I know that this is 1. And when I know that this is 1, I can use the similar triangle to figure out how high that is. Because from the similar triangle, look like much. Oops. If that is 1, the length is 4. If that is 6, that is going to be 1.5, right? So yeah, the magnitude here is 1.5. Okay. And then, you know, one thing I love very much about doing the influence line is that it shows the behavior of your structure. Because let me go to the free page here. You can see if you have the beam like that. Let's begin from the simple beam. Stays the same, even though with the cantilever portion. But when I place the reaction here, when I place the unit load here, the reaction is just going to be equal to that, right? That's how we get 1 at B. But when we look back at this, and I now apply the unit load here, you should see the effect of the overhanging portion. And now you know that when the unit load is outside at the overhanging portion, this R must be greater than 1. For sure, because of the overhanging effect. Right? So it says, excuse me. Hello? So it says pretty clearly that R here must be greater than 1. So you see, this is the value of the reaction at B when your load is now here. Right? When your load is now here. The reaction at B is equal to 1.5. So that makes sense. Right? And when your load moves inside, beginning from B up until D. Kind of fun doing this. This is basically the inference line of a simple beam that you have had before. Can you see that? Okay, so is there any question? Now let's move on to RD, shall we? Okay. Now, when I allow, let's remove this. When I allow RD to move freely, now it is as if I add a roller here, right? So when this begins to move freely, but you still have a roller here, and then you have RD pushing up. It's gonna go like this, right? And then the continuity from here means that this one will come down like that. Okay, so that means the shape of the influence line of RD will look like this. Right? And now not straight. They're trying to connect. Okay, anyway. This is the shape. And now because when you place this doesn't look like D. Let me try it again. When we place the unit load at D, the magnitude of RD is going to be 1. So here right away that this is going to be 1. And again, using the similar triangle because they share the same angle here, right? So using the similar triangle, if I know this is 4, same as above, right? This is 1. This is 2, so this is 0.5. This becomes minus 0.5. So you see, again, it clearly demonstrates the behavior of the structure. When we come back here, when you have the unit load out here like this, because of the seesaw effect, this reaction has to be greater than 1, but in turn, this reaction would have to be, downward, so that in the end, your sigma Fy is okay. So if this reaction on the left is greater than 1 due to the seesaw effect, this one will have to be less than 1, but in the opposite direction, so that in the end your sigma Fy becomes 0. And when it's downward, because we plot the upward forces as the positive for the influence line, because it's natural to many cases, this becomes a negative value to show that when you in fact have the unit load here at this location, your RD is going to be the downward force notice one more thing. You see, when you apply the unit load here, okay? When you apply the unit load here, now you know RB is 1.5 up, RD is 0.5 down. How you notice how when you add 1.5 and 0.5 up, they become 1, right? And which is exactly equal to the unit load. So when you apply the unit load here, RB has to be equal to 1 because the unit load is directly on top of it. And so RD has to be 0. See that? And when, let's say you apply the unit load here, say this is half of that, so here must be 0.5. Because if this is 1, this is 0, that's 0.5. And this is not the very good scale, but you can see that this is half of the triangle, so at midpoint it's 0.5 as well. But in the end, they add up equal to 1. And likewise, at the last point, if I apply the unit load here, you know RD must be equal to 1, and rightly so. And RB must be 0, and in the end, they are in perfect equilibrium. So is there any question? The next one is getting more fun, is the shear at A. Okay. So let me, I think, would it be better if I draw it in the next page? Okay. So A is 1 meter from the free end. Okay. I want to know the shear here this time. So I am going to allow the shear there to go free. Okay. So what would happen? I would place sort of a roller here, right? So that this shear will go free to go up and down, down and up like that. Okay. So now we have two pieces of the free body diagram. The one on the left, it's just the free end with the downward. And on the right, I have this. With the upward. Okay. So look at that. If these forces are allowed to go free, what would happen? Look at this piece. It's just a free piece of member without any support at all. If it is allowed to go free, it would just drop there for the entire piece, right? Let's use this one. Yeah. This one just falls away, right? Just like that. But this one, when you look at this piece, it has two perfectly well placed reactions. So even if you allow this guy to move freely, the right piece here will not move because it has two restraints, right? You try to move it up because it's a shear, so it will not move. So there's no movement on this. So from this, I can say that the deflected shape of this when I allow the shear at A to go free becomes this one. Right? So let us come back to our drawing board here. Okay. Shear at A is simply get to hold on to it. Oh, geez. Right? That's the influence line of VA. So you think that's true? Let us come back and look at what is happening to our structure. Okay? When you look at this beam in particular, and you look at the shear at A, now you have the load here. There would be the shear force at that location, right? Because as long as the load stays anywhere on the left, my free body diagram of this piece would look like this, right? I need to have this. So that becomes the value of the shear at A when the moving load, unit load, moves in this vicinity, this area. But when the moving load move past point A, let's say the moving load is here, I can again cut the same free body diagram because I want the shear at A. I can always draw the shear, the free body diagram out of this portion, right? But when the unit load is not here, on this segment, shear at A is 0, right? Because you don't have anything. So you should probably feel that the section here at A can only be chopped off by the shear force only when the unit load is present, right? When the unit load is here, it tries to chop off section A. But when it's not here, section A is free from harm, right? There's nothing to harm it. So it can move anyway it wants here, but the portion here would not be sheared off by the unit load anymore. That's why it becomes 0. So it makes perfect sense that you only have the value of the shear force at A only when your unit load is somewhere here. Once your unit load moves away from A, section A no longer has any shear. Okay? So, is that okay? Any question? Any question? Let's try one more. We have MA. Because we are at A, let's try MA. Okay? Now let's back see here. Now, if I want, let's move this away. Now is MA. same beam. This time I want moment at A to move freely. Now again, we have two portions. This one on the left with a hinge, right? And another one on the right. Okay. Now this one on the left with the hinge, and then the moment is there, and the one on the right, the moment is there. So what's going to happen to the left? You have a hinge, and then you have a moment. So it would just move like this, right? Because on the left, this is a free end. So when you have the moment, it's just going to move like this. Just going to rotate, just like opening the door. When the moment is in this direction, so your door is opening down like that. But what about on the right? On the right, you have the moment again, but the portion on the right has the perfect reactions. There are two reactions. So when you allow this moment to move freely, the portion on the right will not move at all. So that means the shape of the influence line of the moment at A will look just like this. Oops. Do that again. Right? That's the influence line of moment at A. Just think about it. Again, let's come back to our drawing board because we start this session slightly late. So I'm just going to go over it for a few more minutes. Okay. Let's come back to our drawing board. Okay. When you have the moment on the left, sorry, when you have the unit load on the left, like this, you know that there will be moment here, right? At this location, because when you cut the free body diagram, this is now what you're going to have. Okay. But when the load moves away from point A, moves past point A, let's say it's here, would it be able to bend point A? Or when it moves here, what will happen to point A? Nothing, right? The load moves away, and especially when it reaches the internal span, the portion, the overhanging portion is meaningless now because the load is here. So you have just a simple beam. Only when the load is on the left that, you know, this portion will be bent. Okay. When the load move past point A, oops, got that too. When the load move past point A, now point A may come down, but it will no longer bend. Okay, so no more moment at A when the load moves away, or you can say, you know, the portion becomes just this with no load. It's just a free end, free member without any load acting on it. So that is why the free body diagram becomes just this. I forgot to add the value. So D here, that this is -1, right? Equal to the shear. And right here, it's a bad example, but moment here, because everything is 1, the moment here is equal to the unit load multiplied by the length, which is 1. So it's 1 here. It's not 1 because the load is 1, but it's 1 because the moment is 1. Okay? Oh, sorry. I should erase this. Okay, so let me stop the video before it gets too long.